Semiconductors lie in between conductors and insulators in terms of conductivity. Then the current will actually start to increase very slowly up to a certain point. When it reaches a certain point, the current will increase very sharply. If number of electrons are more, it means that electrons become the charge carrier. This particular current that is produced due to the electric field in between the depletion region is known as drift current. Hey all, I am Hari Krishnan from the Department of Physics, Vidhyaashram PU College, the Temple of Excellence, and we were discussing about semiconductors and the electronic parts behind that. So we were discussing about how and what a semiconductor is, what are the factors affecting that. Now let's see what are the other things regarding semiconductors. So we learned about intrinsic, extrinsic semiconductors, and we learned also that inside extrinsic semiconductors, there are two more categories that is known as N-type and P-type. In those types, the first one we are going to study is known as N-type semiconductors. So what exactly is N-type semiconductors? So again, we know that semiconductors lie in between conductors and insulators in terms of conductivity. In that, we can divide semiconductors into intrinsic, which is very pure. That is, the pure semiconductor is known as intrinsic semiconductors. And then again, we have one more division, that is extrinsic semiconductors. So extrinsic semiconductors means that they are doped with impurities to enhance their abilities. That is, their natural abilities are now modified into some other. So that some other will be determined by the doping elements or simply the dopants. So again, the process of adding impurities is known as doping, and the process of introducing impurities into a semiconductor makes it an extrinsic semiconductor. So while doping, we have two results. One is N-type and the next one is P-type. So what is the difference between N-type and P-type? So that is what we are going to study in this particular session. So first we'll start with N-type. So what is an N-type semiconductor? Again, N-type means it is a negative type. Again, for an atom to be negative, it should have an excess of electrons. And how can you achieve an excess of electron in a semiconductor? Very simple. Since the semiconductors are made of fourth group elements, that is germanium, silicon, and so on. So since they are fourth group elements, if we dope them with a fifth group element, then we can achieve one extra electron in that particular structure. So that is doping with pentavalent impurity, which means the valency should be 5, which means it's a fifth group element. So if you're doping germanium or silicon with a fifth group element, then we will get an N-type semiconductor. So again, the fifth group elements will be arsenic and antimony and phosphorus and so on. If you dope any of these pentavalent impurities into a pure semiconductor, then you will get an extrinsic N-type semiconductor material. So again, the fifth electron will be loosely bound to the parent atom, which means there is an extra electron in the particular atom right now because we are introducing an impurity that has excess of electrons. 4 plus 4, 8, the valency is complete, but since it is a fifth group element, one more electron will be remaining and that particular electron will be loosely bound to the parent atom, which means that it will be available for conduction. It will be just moving around. It will be very ready to move around. So the fifth electron will remain very loosely bound to the parent atom, and ionization energy to free that particular electron at room temperature will be low. Again, it is an excess of electron and the atom is very happy to give it up, so it will be very low. That is, the ionization energy to free that particular valence electron will be very low at room temperature. And what is this Ne greater than, very greater than Nh? So again, in the last class I told you what is carrier concentration. So in carrier concentration, in terms of carrier concentration, here Ne, that is number of electron or electronic concentration, is much greater than the hole concentration, which means that electrons are a lot more compared to the holes that is formed. So we say that, okay, number of electrons are more than number of holes. So how does it matter? If number of electrons are more, it means that electrons become the charge carrier or simply majority charge carrier. Holes still exist, but compared to the electrons, holes are comparatively less. And these holes, as soon as they are generated, it will be filled with the excess electron. So it is much more easier to fill those holes because an extra electron is already readily available. So for that particular reason, we say that number of electrons will be much more greater than number of holes, which also states that since the number of electrons are more, the majority charge carriers or the conduction process mainly happens because of these extra electrons. And the hole and electron recombination rate will be much higher in an N-type semiconductor since electrons are readily available. So again, the rate of electron-hole recombination is more in an N-type semiconductor, and electrons are the majority charge carriers in an N-type semiconductor. And again, since it is one extra electron being added to the semiconductor, we also call it as donor impurity because whatever you're doping it with is donating one electron. So again, we just call it as donor impurity, just something to keep in mind. So again, what will be p-type then? Completely the opposite, right? So again, p-type semiconductors will be formed by doping the semiconductor with the third group elements, which is having a valency of 3 electrons, which means the valency will be incomplete. That is, to complete the valency, you need 8 electrons in the outermost shell and you will only get 7. One will be short. That is, 4 plus 3 will be 7. So we are doping the p-type. To make a p-type semiconductor, we are going to dope the semiconductor atom with the third group elements or simply trivalent impurities. So trivalent impurities can be boron, can be indium, can be aluminum, or anything that you prefer from the third group. You can add that. So you can make a p-type semiconductor just like that. So in the p-type semiconductor, there is more number of holes compared to the electrons in that particular structure, which means that conduction will be mostly carried out by these particular positive holes, or simply because of holing motion, the conduction process will happen. Since that is happening, we say that number of holes will be more than number of electrons. And we can also say that since it is through Holic motion that this particular current is being generated, it will be a weak current or it will be a weak process. So we can say that the p-type semiconductors will be less conductive than the n-type semiconductors, because again holes will be formed and then the electrons will have to recombine, and that particular motion will actually produce the electric current. So the p-type semiconductor, because of that particular lack of electrons, will be less conductive than the n-type semiconductors. Obviously, since n-type semiconductors have more electrons, it will be more conductive. So that is all about p-type and n-type semiconductors. Let us move on to p-n junction. So what is a junction? Junction means when something meets together, it forms a junction. When 2 or 3 roads meet together, it forms a junction there. So what is a p-n junction? Obviously, it's very simple. If you have an n-type material and a p-type material, if you put it together, if you allow it to merge together, then we have a p-n junction, not n-p junction, a p-n junction. Both are right. There is no wrong way to pronounce it, but it's much more easier to say p-n junction. So again, how to make a p-n junction and what are the consequences or special characteristics while forming a p-n junction? That is what we are going to discuss right now. So what happens when you bring in a p-type semiconductor and an n-type semiconductor together in order to form a junction? So again, what are the specialities of p-type and n-type? We already know. One is positively charged and the other one is negatively charged, which means here there is an excess of holes and here there is an excess of electrons. So obviously, when you bring these together, what happens? When you bring these together, obviously, since there is a potential difference, there is diffusion of charges. That is, the electrons that is from this side, the electrons will feel like going to the other side because here it is positive. And all the positive charges from this side will have a tendency to recombine or just go towards the n side, which means from here to here the charges want to flow and from here to here also the charges want to flow, which means while forming a p-n junction, the electrons and the positive holes will have a tendency to cross over each other. But do you think this will happen forever? No. When you merge this, that is during the formation of a p-n junction, some of the charges which are at the very end, the holes and the electrons, will cross over each other. But this only happens for a very short period of time, as when this crossing over happens, it partially creates a barrier here. It partially creates a barrier here so that no additional charges can cross over each other, which means here there will be a region where during the formation of the p-n junction, some of the charges will cross over to the other side and some of the charges will cross over to the other side. That is from p side to n side and n side to p side. Some electrons will cross over, some holes will cross over, and then after some time they will attain a stability so that they will repel any other charges which want to cross over. So when the p-n junction is formed, some of the charges will have a tendency to cross over and some of the charges will indeed cross over to the other side, but only for a short period of time. After a short period of time, this crossing over will stop because then the ions, or simply the positive and negative charges responsible for this crossing over, will create a small barrier in between these two P and N type semiconductor, preventing further electrons or holes from crossing over to the other side. So then after some time we can see that there is a barrier which is formed in between the P and N type semiconductor. So this particular barrier is known as a depletion region. A depletion region. And again, this particular barrier, that is this particular depletion region, prevents further charges from crossing over to the other side. So this again, in terms of electronics, we say that okay, there is a barrier potential that is formed here. So we can also call this as a barrier potential that is being formed, so that the charges or the holes cannot just simply cross over. Now again, it is not meaning that there is only charges in the middle. The middle charges have combined and it is forming a barrier which is keeping rest of the charges at bay. It is not letting the positive charges that is here, it is not letting it cross over to the other side. Just like that, here it is also not letting the negative charges to cross over to the other side. But don't be mistaken, some of the charges might still just creep through here and here. One positive charge might reach here, one negative charge might reach here. That is possible. That is minority, very small number of charges will escape the depletion region. That is very normal. But again, most of the charges won't be allowed to cross over. But let's say that accidentally one positive charge or one negative charge entered into this particular potential barrier. Then what happens? Obviously, since there is a charge difference in between these two, that is, if this is a p-n junction, and this is the depletion region, one side will be negatively charged, or because of the potential barrier, one side will be positively charged and the other side will be negatively charged. So this is preventing the movement of additional charges from entering from both sides. For example, we can say that when the electrons have crossed over each other, it will form a barrier like this. All the positive charges and the negative charges here will form a barrier like this, so that no further electrons can enter here. Just like that, here also all the negative charges and the positive charges will form a barrier here, so that no further positive charges can cross this particular barrier. But since there is a charge difference here, there is automatically an electric field that is generated. Because there is a potential difference, there is an electric field that is generated here from positive to negative. So accidentally, if any charges enter, it will be accelerated. And during the formation of the p-n junction itself, some of the electrons have still gotten in and then diffused to the other side, right? Which means that initially, while forming the p-n junction, there is a small current flow. And if by accident any of these charges seep into this particular region, that is escape into the depletion region, then automatically then also there is a current. So while forming the p-n junction, while forming the potential barrier, the current flow responsible, or simply the current flow that is produced, is known as diffusion current. And if by accident, if any charges get into this particular space and that is accelerated towards the opposite side, because again, diffusion current will be towards this side, and the current, because of stray charges or stray ions being entered into this particular region, barrier potential region, will be in the opposite direction. So that is a different type of current that is known as drift current. So stray ions entering into this particular depletion region will be accelerated in the opposite direction. Again, that is only because the electric field will be in one direction. If any stray ions enter, it will be accelerated in the opposite direction. That's it. So again, barrier potential is just an electric field that is formed around the depletion region. That is, at the both ends of the depletion region, there will be a positive and negative charge, or simply a potential difference that is formed, responsible for the creation of an electric field from positive to negative. That will actually prevent further ions from diffusing from the N side to the P side. So that actually stops the diffusion process, and this happens while the depletion region is completely formed. So the depletion region also has the same function, that is preventing further electrons or holes from entering or crossing over to the other side. So again, the depletion region will determine how the conduction process happens at a p-n junction. That is, if the depletion region is very large, conduction will be very difficult. If the depletion region is very small, conduction will be somewhat more easier, because then you can cross over much more easier. And what prevents the crossing over is actually the electric field, which is responsible to stopping the electrons from moving. So depletion region indirectly controls the electric field, and electric field controls the conduction that is happening inside a p-n junction. So during the formation of a p-n junction, the electrons will move towards the p side and the positive holes will be moving towards the n side. So this particular motion will produce a current, and that particular current is known as diffusion current. That only happens during the formation of the p-n junction. Once the depletion region is set, then the diffusion current will stop. So again, during the formation of a p-n junction, electrons move from n-type to p-type, and due to this happens because of the concentration difference between p-type and n-type. So obviously there is a current flow, and that particular current is known as diffusion current. And similarly, drift current is the current when stray ions, or simply the electric field that is formed at the ends of the depletion region, will accelerate any charges that is entering or trapped inside the depletion region. For example, the electrons from the n side move to the p side, and holes from the p side will move to the n side. If this is the depletion region, if electrons from the n side, if accidentally it enters into the barrier potential region, if it crosses the barrier potential region and reaches the depletion region, due to the electric field difference, this will be accelerated towards the other side, producing a current. So again, we can say that this particular current that is produced due to the electric field in between the depletion region is known as drift current. And one important thing is that drift current will be in the opposite direction to the diffusion current. Diffusion current will be in one direction, and drift current will be in the opposite direction. Now that is all about the PN junction. Now let's learn about the electronical part in that particular concept. That is, using a PN junction, how can we apply that in real world? So again, a PN junction just means that it is a diode. Diodes you have already seen and you have already learned about diodes. Diodes are simply of many kinds. For example, the light emitting diode, which you already knew, and the matrix LED headlights, which you already love, and similar other kinds of diodes are already existing. Even transistors are also a form of this combination of semiconductors. So diodes are just simply a PN junction. Or simply we can say that when two types of semiconductors are formed together, we get a diode. So while bringing while bringing a p-type and n-type together, we have a diode. So this particular diode is known as a semiconductor diode. The diodes which you are very familiar with is an LED, that is light emitting diode, which you have already learned in your high school. So just like that, we are going to learn how a PN junction diode actually behaves. So before that, we need to know how we represent a PN junction diode. So this is the representation of a PN junction diode. So again, this will be the negative part and this will be the positive part. This again, you will do it in your lab as the experiment for semiconductors, that is forward biasing and reverse biasing. So before doing it in your labs, you have to know the theory. So what exactly is biasing? What is forward biasing and reverse biasing? So again, this is the electronic symbol. That is, while drawing a circuit, this is the symbol that we are using for semiconductors, and this will be the negative side and this will be the positive side. Now, what exactly is biasing? So biasing actually means that it is the process of applying external voltage to a diode. So imagine that this is a semiconductor diode. So that is a PN junction. So if I apply a voltage to this particular diode, then we can say that, okay, this particular process is known as biasing. And depending whether I am connecting the positive side to the positive side or positive side to the negative side, we have forward biasing and reverse biasing. So that is what is forward biasing and reverse biasing, depending where the battery is connected. If positive end is connected to the positive end and negative end is connected to the negative end, we say that that is forward biasing. And if the positive end is connected to the negative end, and if the negative end of the battery is connected to the positive end of the PN junction diode, then we see that this particular arrangement is reverse biasing. So that is the two types of biasing. Biasing just means allowing or just simply connecting external voltage supply to a PN junction diode. So again, forward biasing and reverse biasing. Forward biasing means positive to positive, negative to negative. While connecting positive to positive and negative to a PN junction diode, what exactly happens is that since positive to positive connection is made, it squeezes in all the positive charges and it makes it go to the other side, which means the depletion region now, which was larger at first, is now shrunken to a minimum value, which means the depletion region thick, conduction is very difficult. If depletion region is very thin, conduction is very easy. So we can say that the depletion region for this forward biasing PN junction diode is very thin, which means conduction is very easy. And the effective barrier potential decreases. So again, since the depletion region is thin, barrier potential also is very low, which means the diode actually can conduct electric current. And again, forward biasing means that it is positive side is connected to the P side and the negative terminal of the battery is connected to the N side of the semiconductor diode. And similarly for reversing bias, everything will be flipped. That is, the depletion region will be large as the connection is reversed, and negative side will be connected to the P side of the semiconductor diode, and positive terminal will be connected to the N type of the or N side of the semiconductor diode. And then the potential barrier increases, which means conduction will be very difficult and very small amount of current will be there. That particular current will be a reverse current. That is, some electrons will be still trapped in the P side. Again, during the formation of the PN junction, I told you crossing over of charges or ions will be present. Because of that particular reason, 1 or 2 or 3 electrons will be there on the P side. Because of this, when the electric field is applied, these electrons which are trapped on the P side will actually be accelerated. So because of these particular very small minority charges, there will be a small current, and that particular current is known as reverse current. So this much is about reverse biasing and forward biasing. So since we already studied about forward and reverse biasing, what happens during that particular stage? That is, when we connect electricity or allow an external voltage to be connected to a PN junction diode, what is the voltage versus current characteristic? So how will a PN junction diode behave? So actually, during forward biasing, it is very simple. The current will start to increase very slowly. So the current, that is, if this is V versus I, then the current will actually start to increase very slowly up to a certain point. When it reaches a certain point, the current will increase very sharply. So this particular point where the current will increase very sharply is known as the cut-in voltage, or simply the threshold point. So this particular point where the current increases very sharply is known as a threshold point, or simply the cut in voltage. So again, this is V and this is I. So this is I and that is V, which means the current will be laid out in the y-axis and voltage will be laid out in the x-axis. And this is actually indicated in milliamperes. So milliamperes is the scale, or simply the measurement that is used to detect the current flow between a PN junction diode when it is in forward bias. Now what about when it is in reverse bias? And again, in reverse bias only small amount of current will be present, but again it will be due to the minority charge carriers, that is because of the electrons trapped on the p side. And this current will be very small, so that we are measuring it in microamperes. So remember, even though this is laid out as a single graph, it is actually two different graphs where one is in milliamperes and the other one is in microamperes. So again, here also the current will actually be saturated up to a certain point, and after a certain point there comes a sharp increase in current. That particular increase in this particular direction is known as a breakdown region, or simply it is known as a breakdown voltage. So here in this particular value, the breakdown voltage occurs, or simply the breakdown region is achieved. So during reverse bias, current is very small, usually in the range of microamperes, and remains constant, that is known as saturation current. And after some time, if you still increase the voltage, what happens is that the voltage is increased and it achieves what is known as a breakdown voltage region, or simply the current increases very sharply. So this is the VI characteristic you have to understand about a semiconductor diode when it is connected to external voltage. Earlier you used to have Zener diode and a couple of more characteristics, but now it is all removed and only this much is left there to study. So one more thing, since we discussed what is VI characteristics, since we discussed voltage versus current, we have to say something about the resistance. So again, in an PN junction diode, there is no such thing as fixed resistance. It is always changing. So since it is always changing, we can see that we cannot define a fixed resistance for semiconductor diodes. We can only define what is known as dynamic resistance, which means according to the parameters, the resistance value also will change. So since that is the case, we say that dynamic resistance R will be equal to the small change in voltage versus the small change in current. Or we can simply say that R is equal to delta V by delta I. The ratio of the change in voltage to change in current will give you the dynamic resistance at that particular instance. Now, the next topic is half-wave rectifier. So what is a rectifier? I had told you like in the previous classes and the previous sessions also, the AC current which is reaching from the post, or simply from the post, here one connection is coming and that particular connection or that particular line is carrying AC current into your houses. So here inside your houses, you're charging your mobile phone. But when you're charging your mobile phone, it only takes in DC. That is, your phone only takes in DC. So what happens to the AC current that is reaching your house? How is it converted to DC? That was the question that I asked in the previous sessions. So again, the answer is in the last chapter, that is rectifiers. So rectifiers are actually devices which convert this AC current into unidirectional DC current. So this conversion of AC current into DC current is using a rectifier is known as rectification, and the device used for this rectification is rectifiers. Now we have two types of rectifiers. One is half wave rectifier and full wave rectifier. So what is half wave rectifier? So what exactly is a half-wave rectifier? So half-wave rectifier can be represented using this simple particular diagram. Again, you will have your AC voltage source. Again, for AC, there is no positive and negative because it is switching in between positive and negative, alternating its phases. So again, it is connected to a primary coil and secondary coil, which you have already learned. And from there, the connection is made to the semiconductor diode. And it is connected to one end, is connected to the positive end, and from the negative end, it is connected to the load resistance. This particular load resistance symbolizes whatever thing you're plugging it in. For example, if you're plugging in your phone, then inside your charger, there is one rectifier just like this. That is not a half-wave rectifier, it's a full-wave rectifier connected to a capacitor, but the theory is the same. So again, this particular load resistance symbolizes or represents whatever thing you are connecting, may it be your phone, your toaster, or whatever it is. Connections are made as such. So again, there is only the AC voltage coming in, mutual induction, and then simply a semiconductor diode and a load resistance. So how is rectification achieved? That is very simple. That is, when AC current is traveling through this particular semiconductor diode, for 1 second, that is for the positive half cycle, that is when this part of the wave is reaching the semiconductor, it is in forward bias, which means positive and positive is connected, negative and negative is connected, which means the depletion region is very thin, which means the semiconductor diode conducts or allows electricity to pass through it, and the current will reach this particular load resistance. So we can see that when positive half comes, this positive half is only allowed to pass through. Now, what about for the negative half? When the negative half reaches the semiconductor diode, now positive and negative is connected, which means the semiconductor diode is in reverse bias condition. When it is in reverse bias condition, it does not allow current to pass through. Generally, it does not allow, and very small quantities of current may seep through, but it is very rare. So we can say that the negative part is not allowed to pass through. So during the negative half cycle, nothing is allowed to pass through. Then again comes the positive half. Then again, only the positive half is allowed to pass through. So which means only the positive halves of the alternating current is allowed to pass through, while the negative parts are cut off, which means it is filtered out. So we can say that that is how it converts. That is, half-wave rectifier converts an AC current into DC current, which means we cut off the negative part and only the positive bits remain, just like this. Only the positive bits remain. Since it is eliminating half of the waves, that is why it is known as a half-wave rectifier. So again, no conduction during the negative half cycle because it is in reverse bias condition. And during the first half cycle, it will be in positive, that is forward biasing condition. Current will conduct, and the output will be of this particular nature, or simply the frequency will be same, but it will be eliminating all the negative halves. The drawback of this particular rectifier is that it is not actually, if you convert this waveform, it is not actually one straight continuous line. It is a bumpy road. So it is not converting and giving you full DC. Half of the AC current is being wasted, which means the negative half is not being filtered out. So again, because of that particular reason, since the negative half is removed and not filtered and let through, we are only getting this bumpy design. So because of that, we invented what is known as a full wave rectifier. So again, for a full wave rectifier, we have to filter out, or simply we have to let the negative part also be converted into a positive half cycle so that we can let it through. So how do we achieve that? So we achieve that by doing a simple trick that is known as center tapping. You don't need to know the word, but again, the process is known as center tapping. That is, the load resistance RL is actually connected like this in the circuit. Instead of connecting here, we are connecting it to the center. So this particular process is known as center tapping. You only need it if you are going for higher order physics like engineering or any other fields. So again, if you are doing this, then what happens is that the positive half cycle here is allowed to pass through. Just like that, here also the remaining half is allowed to pass through, which means both of them conducts simultaneously. That is, to be more precise, when voltage is at A is positive, D1 conducts. So this is D1 and this is D2. So what exactly happens is that when current reaches this particular point, that is the AC current, when it is reaching diode D1 and D2, both of them will be in their positive half cycle, which means just by using the center tap method, we can just get the full wave output form. That is, when D1 is positive, it lets the positive half cycles pass through and it will allow conduction from C to D. Just like that, when D2 is positive, it allows conduction from C to D again, which means the positive wave cycles are allowed to pass through the diode D1. Just like that, the negative half cycle also is converted into the positive half cycles and it is allowed to pass through. So using this particular center tapping method, we can convert full wave AC into DC. And again, this will be the form of the AC current which is converted. The only difference will be that the frequency of the output will be double that of the input. And again, this is not a direct current form, right? If you have direct current, it will be unidirectional like this. But this is all bumpy like this. So in order to convert that bumpiness, in order to avoid that small AC nature, what we can do is actually connect a capacitor in parallel to this particular circuit. So if you connect a capacitor parallel to this particular circuit, then that particular AC nature will also be avoided. So that is all about full wave rectifier. So again, just to brief, we can say that when voltage at A is positive, D1 will be conducting. When voltage B is positive, D2 will be conducting. Frequency will be double, and if you connect a capacitor in parallel to that particular load resistance, then we can see that it will filter out the AC element in that particular circuit. So that is all about full wave rectifiers. With that, we are finishing up our last chapter, that is semiconductors and semiconductor electronics. So until I see you again, thank you.